Hello and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
And that's definitely me. And I am Corinne Caputo, writer, comedian, and friend to the universe, for sure. This is a big week in gossip world, although I'm dating myself now because, Moiya, do you watch any of Bravo's reality shows?
I do not.
No, but there's a lot of gossip going on.
But not because of my age.
No. But I'm saying this episode's going to come out in a few weeks, so I'm thrilled to be existing in the universe right now because there's some good, juicy gossip going on. And hopefully by the time this airs, there will be even more.
Oh, interesting. Yes, the universe does like to provide good gossip for its best buds. I am another one of those best buds. Hi, I'm Dr. Moiya McTier. I'm an astrophysicist and a folklorist. And the universe has thrown some juicy gossip my way, mostly not from Bravo. Just from Love Island.
Oh.
I feel like the universe makes it dramatic just for me.
Yeah, sure. I feel like I'm literally always talking about TikTok, but this is how I spend my evenings. I saw a TikTok of a woman who was announcing to her boss that she just got cast in Love Island and needs to take 6 weeks off.
Mm-hmm. I always wonder how that conversation goes because there's someone on this season who's a teacher. He's like a middle school teacher.
What is that?
First of all, how do you just take off?
I know.
It's not like it's summertime.
Yeah.
They're just taking off to go be on Love Island. Second of all, no way in hell would I ever respect a teacher again if I saw them doing the shit they did on Love Island.
You're completely correct. It's just too weird.
Yeah, seeing your teacher make out with people, seeing your teacher flirt with people, seeing your teacher get shot down by people, it's just too much.
Seeing your teacher at the grocery store is strange enough. They exist in school and only in school. And in fact, they sleep there. So
yeah,
there's no...
And they should always be wearing long pants. I don't want to see a teacher's knees, but I can see way more than just his knees.
Yeah, you're seeing a whole lot.
A whole torso. That's too much.
I feel like when you're a teacher and you go on a reality show, you use that as a way to be charming. You're like, well, I'm a teacher, so I must be a good person.
Right. Yeah. Oh, I work with the kids, the youths. They love me.
Exactly.
Anyway. I love Love Island so much, but we're not talking about Love Island in today's episode.
That's our other podcast.
Oh God, I wish. I do want to do an Exolore episode about Love Island, actually.
That's so fun.
That's the thing I have to do, but in the future. But today we are talking about exoplanets and how astronomers find them. But we are doing that at an F1 racetrack.
Yes, we are.
Because planets go around stars and cars go around this track.
I love that.
And I thought it'd be an appropriate place to record this episode. So we're in the stands. It's between races right now. Mm-hmm. The last one was very exciting, or at least as exciting as it can be to watch cars just go around the same track many times. But people are drinking, people are screaming, people are having a really good time. Mm-hmm. And there's going to be another race, the big race of the day is coming up in about an hour.
Perfect timing.
I know, right? So let's talk about how we find exoplanets. I know that we have, I think probably in 5 or so many episodes that we've done, I've said we're going to cover an exoplanet detection methods in a future episode. This is that episode.
Today's the day.
Today's the day. We finally made it here. We survived. It is our 20th episode.
This is a huge deal.
Mm-hmm. And for our 20th episode, I figured we should talk about something that is very near and dear to my heart. I studied exoplanets in undergrad and grad school. It was a big chunk of my PhD dissertation. This is the stuff that when I close my eyes at night, instead of counting sheep, I just picture exoplanets. I just picture us discovering more exoplanets. I love these things. So I want to tell you how we find them.
I'm so excited to hear. I mean, you get so excited about so many topics, but I love the ones that are near to your heart.
You will have to keep me on track, Corinne, because I might just get too giddy
Okay.
about exoplanet stuff. So please keep me on track. I want to start, of course, as I do with many episodes, with a bit of a history lesson. The first exoplanet ever was discovered in 1992, though by that point we had been thinking about exoplanets for actually hundreds of years. Ancient humans were thinking about the potential for other planets out there. Scientists in like the Renaissance era and the whatever came after the Renaissance era, they were thinking about planets around other systems. They were starting to think about whether or not life was on the other planets in our solar system. So it was just a natural next step to start thinking about exoplanets. But we found one for the first time in 1992. It was two astronomers working together. One, Alexander Wolszczan.
Yeah.
It's WOLSZCZAN.
That's a
Wolszczan?
wolves. Yeah. You know what? You said it right.
Thanks.
I'm not even going to try.
The other scientist involved was Dale Frail.
Dale Frail. Oh,
The easiest
no.
name we've ever said on this podcast.
That is so opposite.
I know. Dale Frail and Alexander Wolszczan were studying pulsars. Pulsars are neutron stars, which we talked about in the stellar types episode. Neutron stars are the extremely dense remnants of massive stars that aren't quite massive enough to make a black hole. But these are specifically neutron stars that emit radio waves at regular intervals. And so scientists started referring to them as pulses. And so because they pulse, they are called pulsars.
Nice.
We're so good at naming things. They were looking at the pulsar. I'm going to say its name, and be warned, it is just a string of numbers and letters. PSR B1257 plus 12.
Yeah.
Which actually probably tells us the coordinates, the location of this pulsar. That's typically how these long, stringy names get produced. So they were looking at that pulsar, which is about 2,300 light years away from our solar system. And the cool thing about pulsars is that their pulses, these radio wave emissions, are so regular that we can time things based on them. There are arrays of pulsars in space that we call pulsar timing arrays, and we use it to get even more precise timing measurements than we can with like atomic clocks here on Earth.
Wow.
They are extremely regular. And so these two scientists were looking at this pulsar, and they noticed that the pulse became irregular every once in a while, which is weird because pulsars are so regular. But another level to that weirdness was that the irregularity in the pulse came back regularly. It was a regular irregularity.
Oh, interesting.
So they were like, something is happening to this pulsar, or something is around this pulsar that happens periodically, that happens on a set frequency. And so because people had been thinking about planets, that was one of the things they tested. And what they found was that this pulsar indeed had two planets. The two planets were both a few times more massive than the Earth. And after that, it was just like, it just opened the floodgates for finding planets. So that was 1992. People were excited, but not super excited because it wasn't a normal star. It wasn't a main sequence star. It wasn't a star that was fusing hydrogen in its core. So the first time we found a planet around one of these normal main sequence type stars was in 1995,
Wow.
which is the year I was born.
Yay!
So I like to say that I have never lived in a world that didn't know about exoplanets around main sequence stars. Well, I've never lived in a world that didn't know about exoplanets at all, but I love that I was born the same year my field of research was born.
That's very cute.
Yeah,
That's
I know.
really. I guess I was around for 1 year before the exoplanets were born. Wow. I'm
Nice.
so old.
Well, only on TikTok, Corinne.
Only on TikTok.
Only on TikTok and when you're texting your little sister.
Exactly.
So it was in 1995 that we found this first planet around a main sequence star. That main sequence star was called 51 Pegasi, and it's a kind of sun-type star. It's just a little bit more massive than the sun. And this planet was discovered by Didier Queloz and Michael Mayer, both of whom jointly won the Nobel Prize in physics in 2019 for discovering the first main sequence type exoplanet. The planet itself was a hot Jupiter, so it was about 70% the size of Jupiter, though it was more massive, and it orbits the star every 4 days. It's extremely close to this star. It's almost grazing the surface of the star.
Wow.
And they discovered this planet with the radial velocity method, which I covered a bit in the redshift episode, but we're going to talk about it again later in this episode. So after 1995, what commenced were a couple decades of an intense era of exoplanet discovery. People just wanted to find as many exoplanets as we possibly could, and it was really hard for us at that point to characterize these exoplanets, meaning it was hard for us to determine the physical properties of these exoplanets. But then we moved into the era of exoplanet characterization, and I basically started doing exoplanet research right around this time when we were developing more methods and the telescopes were getting good enough to really start characterizing these exoplanets so we could learn more about their atmospheres and their surfaces and maybe even something about their internal processes. So now we are in the era of exoplanet characterization, and I think soon, we're these eras are overlapping, but we're getting into a time when we have discovered enough exoplanets that we can now do cool population statistic studies on them. So as of today, when we're recording, it's March 6th, 2023. As of today, astronomers on Earth have confirmed the existence of 5,272 exoplanets.
Whoa. Now, is that changing? Do you think that's going to change by the time this comes out? Or is it changing that frequently?
Yeah.
Wow.
Yeah, I think that we will be a few off by the time this episode comes out on the 20th.
Wow. 27.
On the 27th. Well, even more. We'll have found even more.
We'll be really off by then.
No, it was a big deal when we crossed the 5,000 mark, because when I was in grad school and I was giving talks about exoplanets, I would always say we found about 4,000 exoplanets.
Oh, wow.
And around the time that I graduated, we crossed the 5,000 mark. And now it's like 300 planets later. We're finding new planets all the time. And there are also thousands of exoplanet candidates that are waiting to be confirmed.
Cool.
Because you can't just look through a telescope, see something you think is a planet and be like, yep, I found a planet. No, there's a whole process.
Yeah.
You have to discover that exoplanet. You have to do your due diligence as a scientist to make sure that it's not some other thing. Then you have to confirm that planet by looking for it with another method, or at least with a different telescope, just to make sure it's not some weird, funky thing that your telescope is doing. And then you have to write a paper about it and put it out into the community to be peer-reviewed and potentially ridiculed if you're wrong and other people discover that you're wrong. So there's this whole process to it. There are thousands of candidates just waiting to be confirmed, which is why I'm confident that by the time this comes out, there will be more exoplanet confirmations.
That's so fun.
So now we're going to get into the different methods. There are a handful of them. Most of them haven't actually found that many planets, but we're going to talk about most of the methods here today. Any questions before we get started with that?
No, I'm just thrilled.
You're just ready. Okay. So often when I am giving a talk about exoplanets, I don't want to just tell people how we find them. I like to do some crowd work and ask people how they think we found exoplanets. And I'd say about 80% of the time, when I ask an audience, how do you think we find planets? Someone will say, take a picture of it.
Yeah.
That is extremely difficult to do, but we have done it. This method is called direct imaging, and it is exactly what it sounds like. You take a telescope, you point it at a star. You do have to block the light of the star because it's too bright, and it will overpower any signal from a planet. But you can block the light of a star with an instrument called a coronagraph. I think we've talked about them before on the pod. Probably in the eclipse episode, I'm guessing. So you use a coronagraph, like put it over the body of the star and block its light, and then you can see other more faint light sources, like a planet. And this works best for planets like hot Jupiters, really big planets that are kind of close to their stars, especially ones that are hot in and of themselves, because they will emit in the infrared. So they're actually emitting their own type of light. But we really have only found like 100 planets using this direct imaging method because it's so difficult. You know, a star is going to be thousands of times brighter than even the hottest exoplanet.
Yeah.
So it's really hard to do. But I'd say the first directly imaged exoplanet was discovered in 2004 and then confirmed a year later, because remember, there's this whole long confirmation process. And that that exoplanet was called 2M1207b. Of course. It was the first exoplanet that was directly imaged and the first exoplanet discovered orbiting a brown dwarf star. I don't think we've talked about brown dwarfs before on this show.
I don't think so.
But a brown dwarf, some people will call it a failed planet, but I don't, or a failed star, but I don't like either of those. But it is something that is a ball of gas like a star, but it's not massive enough to do the typical hydrogen fusion in its core. It does a slightly different type of helium fusion in its core. There's a whole research group in New York City that's based largely out of the Museum of Natural History in New York called BDNYC, Brown Dwarfs of New York City. They do really good work. They would not like it if I called a brown dwarf a failed star. But brown dwarfs are like between the mass of Jupiter and a low mass star.
Yeah, that makes sense. That is the way that I would have guessed we do it. Mm-hmm. But obviously there's more to it.
It's the most obvious. It's the most straightforward. And the only reason we haven't found more planets using this method is because planets aren't bright. And when you're taking a picture of something, what you're doing is capturing light from that object. So if these planets aren't very bright, we're not going to be able to take a picture of them.
Right.
But luckily, there are a lot of other methods that we can use. And the next one is my favorite method for finding exoplanets, and it's called transit photometry.
Ooh.
I love this so much. So transit photometry works by, let me break it down. Transit is when a planet passes in front of a star from our point of view. And the geometry is really important with all of these observation methods because there's no guarantee that a planet would be orbiting in the right plane around its star for it to pass between us and the star. Like it could just be off plane, right? Mm-hmm. So we have to get very lucky with the orientation of these planets, which means there are many planets that will never transit from our point of view. There are many planets that we could not discover using the transit photometry method.
Interesting.
Mm-hmm. So a transiting planet really is its own category of planet, but it just has to do with how things happen to be oriented in space. So that's the transit part, when a planet passes in front of a star. The photometry part tells you what type of information we're collecting. Photometry, which means we are measuring the amount of light. Transit photometry method works by having a telescope stare at a patch of sky and measure how much light you're getting from that patch of sky. And if you have pixels in your camera, then you can get really specific about light from individual stars in your field of view. If a planet transits, or if it passes in front of the star, it will block some of that star's light. And when you graph this out, you see a beautiful curve that we call a transit light curve. And we can study that transit light curve to learn all kinds of things about the planet. We can, depending on how often the curve happens, if you observe the system long enough, you'll see multiple transits. And the time between transits is the length of that planet's year.
Cool.
So you get the period of the planet. And because Johannes Kepler was kind enough to give us Kepler's third law, if you have the period of the planet and you know how massive its host star is, you can calculate how far away the planet is from its host star.
I love that. I love when we use information to inform other information.
Yes, that's all of astronomy. Yeah. So you can then calculate the distance from the star. If you know the distance from the star and you know how bright and hot the star is, you can also calculate like an average temperature. We call it the equilibrium temperature for a planet. So you can get an idea of how hot or cold the planet might be. There are so many cool things you can learn. You can learn the size of the planet from the transit because the depth of that curve is basically just like the fraction of the star's body or the star's surface that the planet is covering. This is just like algebra and geometry.
Yeah.
And I love that math that I learned as a 7th grader helped me get a PhD in astrophysics.
Yes. See, it does come in handy.
It really does. It does. Even if you don't become an astrophysicist, the math that you learn in your algebra and geometry and trig classes, it's still all very useful.
It really is.
The first transiting exoplanet was seen in 1999. And it was another hot Jupiter. You might notice this trend that many of the planets we found first were hot Jupiters because they're the easiest planets to see.
Yeah.
They're the biggest ones, so they will block more starlight. They're the most massive ones, so they will tug on their stars more. And they're hot, so they're emitting their own infrared light. So we have a chance of taking an actual picture of them, which is why they dominated the exoplanet detection era for a few years. But it was 1999. This hot Jupiter is orbiting a star called HD 209458, which is a sun-like star about 150 light years away from us. The planet was originally detected with radial velocity, which is the next method we're going to talk about. But then it had to be confirmed, and it was seen in transit by 2 separate teams. One of those teams was led by Greg Henry. I know nothing about him. The other team was led by Dave Charbonneau, who I was advised by in undergrad. And there is somewhere, I'm going to try to find it. He was the professor in charge of my undergrad senior thesis class. So I had to turn my thesis into him. And I was going to say I suck, but no, I'm fun. So I printed out my thesis. I had to hand in a physical copy. I printed out my thesis and wrapped it in a blanket like I was swaddling a baby. And then I made Dave Charbonneau, who is like 6'5". He like towers over me. I used to get extremely intimidated talking to him because he has this habit of like, he'll say something and then he'll stop talking.
Yep.
And I felt like I should say something, but I never knew what to say. But like, he's just one of those people. He has a very commanding presence.
There's a presence, yeah.
And so I made Dave Charbonneau one of the first people to ever detect a transiting exoplanet, this 6'5" intimidating man. I made him pose with me and my thesis baby as if he was like a very proud grandpa.
Aww. As he should have been.
As he should have been. And he was such a good sport about it. So yeah, Dave Charbonneau, great guy. And he was one of the first to see a transiting exoplanet back in 1999. And now the transit photometry method is by far the most successful method for detecting exoplanets. So I said that we've confirmed about 5,300 exoplanets, 5,272 to be exact. 3,945 of those confirmed planets were discovered using transit photometry.
Cool.
It's like most.
Yeah.
Definitely most of the planets have been found with transit photometry. And that is due in large part thanks to missions like Kepler and TESS. So Kepler, named after Johannes Kepler, was launched in 2009. It's a space-based telescope. For 4 years, it stared at a single patch of sky and measured how much light we were getting from it. And that's like called the Kepler field of view. You can look it up where it is. And then this really tragic thing happened to the Kepler Space Telescope. It had these 4 reaction wheels that would stabilize its position in space so it could stare at that one patch of sky continuously. But in 2013, 2 of its reaction wheels broke. So it wasn't able to stabilize itself anymore. But the fucking geniuses who are in charge of the Kepler mission, can you tell? I've loved this. They figured out a way to use the 2 remaining reaction wheels along with the solar wind, pressure from the solar wind, to kind of stabilize the Kepler spacecraft. So instead of looking at a single patch of sky, it would look at, I want to say, 13 different patches of sky all along the ecliptic. And the ecliptic is like the plane of the sun's apparent orbit around the Earth, because it was using wind from the sun like at its back to stabilize it. Like, if that makes any sense. Like, it's like the wind is at its back and its two wheels are in the front, just like making sure that it's always facing away from the sun.
That's really fun.
It's so fun. It's so cute. And so Kepler had this second life as the K2 mission, which was less stable. So you're getting less data from all of these stars, but it then gave us information about exoplanet populations in different parts of the sky, which was really cool. So I have used so much data from the Kepler spacecraft, and I love it so much. And I was really sad when it was officially decommissioned in 2018. But it outlived its original planned lifespan. Like, you can make a movie out of this. You can make an epic movie out of the hardworking, determined Kepler spacecraft breaking its reaction wheels and then getting back up and continuing to look at space. I really love it.
Moiya's weeping.
I get so I really am. I get so emotional thinking about Kepler, because I would not be the scientist that I am today if I hadn't used Kepler data.
Yeah. Hi, it's Corinne, and I want to give a shout out, as always, to our patrons who are supporting this podcast. It means so much to me and Moiya and everyone who helps make this show. We really appreciate your support. So thank you, as always, to our Sun-like stars, Sharn Llewellyn, Finn, Ian Williams, and Megan Moon. And you can support us, hear your name on this podcast, and make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. Find the star chart, Patreon info, and more at our website, palebluepod.com, or by going right to patreon.com/palebluepod.
The fact that you're listening to this show tells me a couple things about you, and I can recognize those patterns because I am a scientist and an analytical thinking genius. But here are the things I know. 1, you're listening to an astronomy podcast, so you clearly like to learn. But 2, you're listening to specifically this astronomy podcast, which means you like to learn in fun and friendly and interesting ways. So please let me tell you about Brilliant.org, which is the best way to learn math and science interactively online. Brilliant has thousands of lessons in math, science, and data analysis, and they're adding new ones every single month. Brilliant doesn't just teach you facts and formulas. They actually help you develop your intuition for these subjects through interactive gameplay. So their science courses can help you get a deeper understanding of things we talk about a lot on here, like planetary orbits with their classical mechanics lessons, or particle physics with their quantum objects course. Whatever you learn on Brilliant, you'll have a fun time doing it, and it will strengthen your general analytical thinking skills, even outside of the specific topics that you're learning about in your lessons. So you, as a Pale Blue Pod listener, can get a 30-day free trial by going to brilliant.org/palebluepod. And the first 200 people who sign up using our code will get 20% off their annual subscription. Again, that's brilliant.org/palebluepod for a 30-day free trial. And then if you are early enough, if you're an early adopter, you will get 20% off your annual subscription.
Hi, it's Corinne with a podcast recommendation. Queer Movie Podcast is one of my absolute favorites. It's a queer movie watch party hosted by Rowan Ellis and Jazza John, and you'll have so much fun joining them as they research and rate their way through the queer film canon, one genre at a time. So there's rom-coms, slashers, contemporary art house cinema, black and white classics. It's just a celebration of all things gay on the silver screen. You're going to love it. New episodes of Queer Movie Podcast come out every other Thursday, wherever you get your pods.
We're all about getting cozy here at Pale Blue Pod, and I always feel the comfiest when I can sit back and relax with maybe a good book, but definitely a really good smelling candle. So I'd like to recommend the Queer Candle Company. They're a small batch soy wax candle company. They hand pour their candles with love. They're also queer and trans owned. The candles are topped with a variety of botanicals, including pressed flowers, dried herbs, and zested aromatics. And friends, I got one of the dark plum candles from the Queer Candle Company, and the only way I can describe it, now I don't believe in heaven, but if I did, I am pretty sure that this candle smells like dark, sexy heaven. You know, not hell, because there's not torture, there's not fire and brimstone, but it smells so good, and I want to bathe in this scent. The Queer Candle Company donates 10% of their monthly profits to the Sylvia Rivera Law Project, and they also sell DIY refill kits online so that any of their candles are endlessly refillable. You can use the code PALEBLUE at checkout to get 10% off your first order on their website, queercandleco.com. So go to queercandleco.com, type in pale blue for 10% off, or check out their Instagram and TikTok at queercandleco. Highly recommend the dark plum. Like I said, dark, sexy heaven. What's not to love? So that was one telescope that really made transit photometry so successful. Another one that is more recent is called TESS. It's the Transiting Exoplanet Satellite Survey, or Survey Satellite. And it is also using the transit photometry method to discover a lot of planets. But that's a cool one. It's not looking at one patch of sky. TESS looks at the entire sky regularly. Like it's over and over again taking pictures of the whole sky so we can see how things change in the sky over time, which is really nice. This method, the transit photometry method, is best for planets that are closer to their stars because then it's easier for them to block the light from our point of view. And the bigger the planet is, the easier it's going to be to find, which is why when you look at a catalog of exoplanets, especially ones found with transit photometry, which most are, you have to be really careful about making claims about exoplanet populations in general, because it's really easy to look at these catalogs of discovered planets and think that small planets aren't common.
Sure, yeah.
But really, these small planets are just harder to find. And since one of the big missions, one of the big goals for Kepler was to determine how common Earth-like planets around sun-like stars are, it's hard to find an Earth-like planet, especially around a sun-like star, because we are so small compared to the sun.
Yeah.
So you just have to be really careful about systematic biases in your telescopes and in your spacecraft. That was the big theme of my third year research project in grad school. Beautiful stuff. Beautiful stuff. Do you have any questions?
I wish that I looked back on school with this kind of love.
Oh, to be fair, I also look back on grad school as the thing that made me go through multiple rounds of therapy, get several stress tattoos, and create a crying nest under my desk. But I do love data.
Yeah.
Academia makes the process fucking miserable, but I do love data.
I love that.
Okay, goodbye transit photometry. It really, truly is my favorite. On to radial velocity. So we have talked about radial velocity in the past. Radial velocity is specifically the velocity of an object towards and away from us. So when we were talking in the redshift episode about stars appearing to be redshifted or blue shifted, the redshift is when the star moves away from us along our line of sight, and the blue shift is when the star moves towards us along our line of sight. And we expect stars to be moving towards and away from us because they aren't static beings. They are moving around the galaxy, like they're doing their own orbits. But also if you remove that motion from your data, you can see that stars still dance a tiny little bit around the center of mass of the star itself and any other bodies that might exist in its system. And most of those bodies are going to be planets. So essentially, the gravity of a planet will tug a little bit on the star and make it do a little dance. It'll make it wobble. And in wobbling, it will move towards and away from us, which means that the light emitted by it, if we capture that light and put it through a spectrograph so that we can see the beautiful, usually absorption lines to see the molecules that are being absorbed by the star, you can measure how much those very precise absorption lines shift as the star is moving. And the distance that it shifts tells you the speed with which the star is moving radially. And you can translate that speed, that velocity, into the mass of the planet that is tugging on it. Because the more massive the planet, or I actually shouldn't say it's just about mass, it's also how close they are to each other. But the stronger the gravitational pull, the faster the star will wobble.
Oh, cool. Okay.
So that's essentially how the method works. From that, so with transit photometry, you can learn the size of the planet, like its diameter. With radial velocity, you get a sense for the mass of the planet.
Okay.
Because it's due to its gravitational influence. So this method is best for massive planets that are very close to their stars, like a hot Jupiter, which is why the first planets discovered were done using radial velocity, and they were hot Jupiters.
Cool. Yeah, I was wondering, because it seems like transit photometry and radial velocity are great for these like larger planets, but radial's more about mass and transit is about size. Got it.
It is also much easier to see a small planet with the transit method than it is with the radial velocity method.
Sure.
Yeah. So of the roughly 5,300 confirmed exoplanets, about 1,000 of them, right now the number is 1,027, have been confirmed or detected with the radial velocity method.
Cool. Wow. A fifth.
Yeah, a fifth. I know several people who work on radial velocity missions. You can do this with space and ground-based telescopes. What you need is a telescope to collect light and a spectrograph or a spectrometer to pass the light through so you can see those beautiful absorption and emission lines. But I have never used radial velocity data in my research.
Oh,
actually.
Interesting.
I'm a Kepler girl.
Yeah.
I'm a transit girly.
Yeah, you stick with what you like.
Yes. So that's radial velocity. That has a kind of interesting, complementary companion. There's radial velocity, which is towards and away from you on the line of sight. But there's also astrometry, which is motion.
Astrometry. It sounds like astronomy, but I've had a few drinks and I'm like...
Yeah. So if photometry is measuring how much light you get, astrometry or astrometry is measuring the astronomy of stuff. It is measuring the positions of celestial objects. We have actually only found 2 planets using this method. 2, but we expect to find a lot more in the coming years.
Okay.
And that is thanks to the Gaia spacecraft. So Gaia launched in 2013, the same year that Kepler's 2 wheels broke, R.I.P.
Aww.
Rest in so much power. So Gaia launched in 2013, and it studied the positions and motions, proper motions, motion around the galaxy, of more than 1 billion stars. It gave us the most abundant and accurate map of the Milky Way galaxy that we had ever had before. I also used a lot of Gaia data in my research when I was trying to... So Kepler told me about the relationship between planets and their host stars. Gaia told me about the relationship between stars and how they move in different parts of the galaxy. So Gaia launched in 2013. It has had 3 different data releases so far. And this is the way that telescopes often work. They don't just observe and then spit out a bunch of data and never get used again. Especially these space-based survey mission telescopes, because you can design a telescope to be used for different purposes. But these mission-based telescopes, they have a plan for what they're going to observe. You can't request time on Gaia. They have a plan. and they execute that plan. And at set intervals, they release different types of data. So the first data release had just like the positions and honestly, kind of shitty information about how those stars were moving. With the second data release, it had been observing these stars longer, so it had longer baselines and more precise measurements of their motion. And in DR3, which came out in June of 2022, so after I defended my PhD, which means I used Gaia DR2 for my research. But DR3 gave us more information about the chemistry of these stars, actually, and information like their temperature and their chemical composition. Gaia DR4, which won't come out until on their website it says no sooner than 2025, or like the end of 2025. So no sooner than 2026 can we expect to see Gaia DR4, but it will have time series astrometry data. I made the distinction earlier. I said that it measured the proper motions of stars, so like the motion of stars around the galaxy. If you can remove that motion from your data, then you can see that the very small scale motion that these stars have because of planets tugging on them. And so very similar to the radial velocity method, these planets will make these stars wobble, but they'll be moving like up and down and left to right. And we can measure that motion to figure out the mass of the planet orbiting the star. But we won't be able to do this until like 2026 with Gaia data. But once that happens, they expect to find tens of thousands of exoplanets using the astrometry method.
It's like opening the floodgates.
Really, it really is. I tried to do a project in grad school to determine like how feasible it would be to find planets using astrometry. And it's just really difficult until Gaia releases that set.
That sounds like me Googling, like, when is Succession coming back or something? And it's like, no sooner than this date. It's like... Or like Severance. Yes. Have you watched Severance?
No, I haven't.
Moiya, you gotta.
Is it scary?
No.
It's not scary.
No.
It's dramatic.
It's not scary, but it is kind of mysterious.
Oh, I like mystery.
Yeah. It's not like Sherlock Holmesy, but it is like, what's going on in there? You know?
Ooh. Noted. But yeah, it is very similar. And I think another similarity here, people I imagine have like watch parties when Succession or Severance come back. Astronomers go fucking wild for these
That's what I was
data
going to
release.
ask you. I'm like, is there some kind of like culminating event that's to celebrate? Or is it like on the calendar and it's like, I can't hang out that day, Gaia 4 is dropping?
Yeah. Yes, both. Yes to both. When Gaia DR2 was released, like 100 different astronomers descended upon New York City because the Center for Computational Astrophysics, which is in the Flatiron District of New York, had a Gaia DR2 hackathon where the goal, the objective for the day was to have as many astronomers come as they wanted, download the data, like start as soon as it came out. And Gaia it's not NASA, it's the European Space Agency. So like we were working on European time. So as soon as the data gets released, dozens of astronomers in a room download the data and just start doing science with it. They just start like they have an idea for what they're interested in. They just start doing science, and then they do that for a whole day, and it's just like it's a party to them. I went. This would have been my second or third year of grad school. I went to the CCA hackathon, and I hated it. I hated it so much because I was surrounded by it. Let me back up a second. First of all, it's not as straightforward as it should be to just download data.
Yeah.
You have to know a specific querying language, like a specific type of coding syntax to request the data. So first of all, I couldn't do that. So right off the bat, I felt like an idiot failure.
Yeah.
I had to get the data from a flash drive from one of my advisors. And then everyone around you is doing their science and announcing when they've found something cool. So like every 5 minutes, it's someone who I have looked up to for my career, or also just like a random visiting grad student be like, oh, I found this. Oh, I found that. Oh, I saw that too, but here's something you should consider. And it's just that for a whole day.
That is my nightmare. That is so overwhelming to me.
I left in tears.
Yeah.
Like I stayed until after lunch because the CCA has more money than they
you
need.
gotta get the free lunch.
Yeah, they have really good catered lunches. So I stayed until after lunch, and then I was like listening to people do that. I started crying, and I just left.
Yeah, I'm really glad you left.
Thank you. But I was then able to do my own science on my own time in my own room.
Yeah, exactly.
So that was good. That was good. But I imagine a similar thing happened with Gaia DR3, and it's definitely going to happen with Gaia DR4. I would expect, you can mark your calendars, in 2026, whenever this 4th data release comes out, they're going to have another hackathon, and those fuckers are going to be finding so many exoplanets, like right away. I know it. I can just feel it in my bones.
Yeah, I think you might be right. I'm imagining a Pale Blue Pod live that night, and everybody comes, and we like place people in the audience so at random points jump up and yell a fact.
Oh my God, I might cry and leave. Like, that might be too triggering.
It's too scary.
It's too much. I would rather watch The Ring than sit through another Gaia data release hackathon.
Okay, I know what we're doing. Data release 4 is next, is that it?
Mm-hmm.
Okay, we're all watching The Ring that night. We're all gonna self-inflict some other trauma.
Because that will be less scary to me, for sure. So that's astrometry. 2 planets for now, but give it a couple years, we're gonna find a bunch.
They're gonna catch up.
And then I think the next method that I want to talk about hasn't been super successful. We've only found almost 200 planets using this method, but it is called microlensing. Gravitational lensing is something that people use to study like very distant galaxies. It is a consequence of one of the relativities, probably general relativity, and it says that if you have a massive enough object, it will warp space-time, and light, instead of traveling in a straight line, will bend around this very massive object.
Yeah.
So microlensing is that, but on a smaller scale, where imagine you have a system with a star and a planet orbiting it, but that system is way too far away for us to see. If we get extremely lucky, another star will happen to, or maybe a small black hole, will happen to pass between us and that system, and it will bend the light from that system and like focus it towards our telescopes.
Oh, cool.
Which lets us see systems that are further away than we'd be able to detect with other methods. But the downside here is that it's really just a fluke occurrence. You know, we have no control over stars or black holes passing in front of these systems and conveniently lensing their light towards us. So we can't study these systems again.
Yeah. Interesting.
Which makes the confirmation process a little tricky, but still very cool. The telescope that will be very good at finding these microlensing exoplanets hasn't been built yet. It should be finished in the next couple of years. It's called the Nancy Grace Roman Telescope, named after Nancy Grace Roman, who was the first administrator, or one of the first administrators of NASA.
Oh, cool.
And this telescope formerly was known as LSST, the Large Synoptic Survey Telescope, but they changed its name because apparently you can change the names of some telescopes, but you can't change the names of other telescopes. You can change the name of a telescope from something that is completely innocuous, like Large Synoptic Survey Telescope, not offensive at all, to Nancy Grace Roman. Great, I'm glad she got that. But when you have a telescope named after an actually offensive person, you can't change that name. No.
No, that one has to stay. We can't, it's better to feel bad than...
Of course. I won't subtweet. I will tell you that I am talking about JWST, the Just Wonderful Space Telescope, which is named after a homophobe who worked at NASA in the 1950s and was responsible for persecuting a lot of queer folks at NASA during the Lavender Scare. So, fuck that guy, and let's stop naming telescopes after him, whatever.
Yeah, it is very disappointing. Even if you Google it, it's like NASA refuses to change the name.
Yeah,
and you're like,
over and over again.
Yeah, space is, I think, one of the things that's so fun about it is that it's for everybody, and like, it's not, I don't know, we don't need to be mean or unkind or...
Yeah.
You get it.
We We both get it, but it's nice to say it out loud.
Yeah.
So the Nancy Grace Roman telescope expects to find a lot of these microlensing events because it is going to be looking at the whole sky. It's in Chile. I didn't go to the foundation of this telescope back when it was LSST, but I did see it from afar. We were supposed to tour it, but there was a big storm, so we could not drive up the mountain. So I saw it from afar. And it's going to be looking at the whole sky, and it's like specially tuned to see these gravitational lensing events.
That's very cool. That feels so specific. Isn't that amazing?
Oh yeah. Well, I mean, that's one of the things it's going to. You do not build a multi-billion-dollar telescope unless it can do multiple
one
things.
thing.
Yeah. So that's just one of its focuses. So those are, I'd say, the biggest methods of detecting exoplanets. That's pretty much all of them. There are some others, but they're not really worth mentioning because this accounts for like all of the 5,000.
Yeah.
If you would like to do your own deep dive into different exoplanets and start doing some like cool statistics with it, maybe you can do that thanks to the NASA Exoplanet Archive.
Ooh.
This is an online database operated by Caltech, but they're under contract with NASA. Dr. Jessie Christensen either started the NASA Exoplanet Archive or managed it for a long time. She's a lovely woman. She does cool exoplanet work. But the NASA Exoplanet Archive has data on all of the confirmed exoplanets and many of the candidate exoplanets. And they make it pretty easy for someone without any coding experience to play around with the data. So without downloading anything onto your computer, you can go to the NASA Exoplanet Archive and you can graph different properties of planets. So you can look at the relationship between planet size and planet mass. You can just like graph those. They have information about the size, the mass, the distance from the star, the date discovered, the discovery method, information about the host star. Like they have so much information.
That's so cool.
So I would recommend just going to the NASA Exoplanet Archive site and playing around with it. If you have zero experience playing around with astronomical data, or if you have zero experience like plotting any type of scientific data, it's a good introduction to it, I think, because they make it really easy. There's absolutely no pressure, and you get to learn about cool exoplanet populations.
That's so fun. I love when it's open source.
Yes, this is another thing I love about exoplanets. The study of exoplanets, and one of the reasons I chose it in grad school is because a lot of this data is publicly available. I was able to get through my PhD program relatively quickly because I never had to request observations on a telescope and then like wait for them to be done and inevitably get clouded out with bad weather and like delayed and everything. I just went to Kepler's website and downloaded their publicly available data.
Isn't that the best feeling?
Yeah. It really is. And so if that's something that you are interested in doing, either now or eventually, like a really good place to start is with the NASA Exoplanet Archive.
I love it.
I'm a big fan. What are your thoughts on exoplanets and how we find them?
Well, I think most of my thoughts are in what they are, like what they're like and how close they are to Earth or not Earth or things in our solar system. So I'm thrilled that we're actually finding them. And I'm kind of shocked that I shouldn't be shocked by now that it's so recent, but I mean, there are clearly so many other things in astronomy that we are looking at and studying. It's not like this is on the top of mind for everyone. But I love that we're doing it, and I think it's amazing. I really like your favorite detection method too, transit photometry. I think that's so fun.
Well, it's because I get really excited when I talk about it.
But it's the one that I think makes a lot of sense to my brain. I don't know, it just fits.
Yeah, it's a good intuitive one.
I think that I'm really excited that there are more coming all the time. I think that's really thrilling.
Yay.
Yeah, I can see why you chose it. It just seems to be like a field that's kind of ripe for new discovery and lots of information.
Yeah, it was the field. Like poppin' subfield of astronomy when I was developing my persona as a researcher. And it was like one of the fastest growing subfields. All of the young people in astronomy, that's slight exaggeration, but like so many of the young people in astronomy were getting into exoplanets because it's a field where we know there's going to be a lot of work to do in the future.
Yeah.
So you have like good career longevity if you do exoplanets.
That is how it feels to me, too, of like, this is just the beginning of this.
Mm-hmm.
Yeah.
So exciting. Well, I'm sure we are going to cover a lot of stuff, a lot of other things about exoplanets in the future.
Yeah, I want to hear all
about
about
so much to cover. But yeah, that will be something to talk about in the future. For now, you know how we find the exoplanets, and I think that's pretty cool.
I mean, that's the first step.
Mm-hmm.
And I think, Moiya, look at this. This is perfect timing. The big race is about to begin.
They're about to go around the track like the planets going around the stars.
Exactly. And they're all going to work together to replace the tires, which is something working together is done in astronomy, too.
So many parallels.
So many parallels. Okay, so for everybody listening out there, just remember, you are space.
Yeah, you are. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.